Hello everyone, this is part 5 from the compression steel, and we're going to work out this problem here. So the problem reads, it's a design problem though, so the problem reads a 25-foot long column has one end rigidly fixed to the foundation. The other end is braced in the weak axis and free to translate in the strong axis. It is subjected to a dead load of 120K and a life load of 220K kips, right? Design the column using this type of, let me grab my laser, a pointer, this type of steel, A992 is this type of steel. So first, we need to understand the problem statement before proceeding with the solution. First, we have an I-beam column that looks like this, 2 flanges and a web, right? If we look at the column from the top view here, we have the x-axis and we have the y-axis. The x-axis is the strong axis, and the y-axis is the weak direction or axis. If you're still confused on which one is the strong and which one is the weak, you need to watch my previous lectures on, on this topic to so you can come back to it here. So I'm just going to assume that you are aware of which one weak and which one strong, which directions. Then the problem statements here emphasize the idea of that the other end is braced in the weak axis. That means the I-beam is braced from this side and this side. So the y-axis is a non-sway column, while the strong axis is a sway column. So the x-axis is non-prevented from sway, which means a free sway, and this one is a prevented, right? Like if we have an I-beam here attached, an I-beam here attached, then no swaying on this side here. So this is what the problem says. To start with, and again, it's a designer problem. I apologize for all this mess here. I just find it more efficient to lay down all the solution ahead of time so we can communicate the information easily. So because the weight of the steel is not given, the weight of the column steel is not given, we're just gonna assume it is 100 pounds per foot. Because now we are dealing with kips, so we're just going to divide this by 1,000 to make it 0.1. So then the weight of the column is 25 feet long times the 0.5, which is the assumed weight, and it gives me 2.5 kips, and this is the weight of the column. Then the factor design load, which is PU, is 1.2, right? This is the factor load. It's 1.2 times 120, which is the dead load given in the problem statement, plus 2.5 weight of the column, plus 1.6 times 220, the life load. And this gives me 499 kips, which is the factor load on the column. So then we're going to have to design the column for a column that can bear more than this load, because this is the breaking point. This is where the column is going to fail or buckle at this weight. So then what is the area that aligns or that aligns with this load here? The gross area is the PU over the phi times Fy. So the 499 that we just found over 0.9, the phi times 50, the Fy, and it gives me 11.1 in squared. That's the gross area where the column buckles at this load here. So if we're going to design a load, that means we're going to have to find a gross area larger than this and can bear more load. So then if we go to page 435 actually, and the table, we find the W-shaped dimensions. The first column is the shape, the type of sections that we're supposed to use or select, and the second column is the gross area. So we're going to compare all the gross area to this, the found gross area here, and find something larger. Now, what the book did here was the book selected gross area larger than this, way larger, 17.9, just so we can be conservative and also have a buckling mode here. So because of this gross area selected 17.9, the section selected is W14 times 61. So from page 435, if you look at the second column, which is the area, gross area, and find 17.9, and then look at the left, you will find the shape that's equivalent to it, which is W14 times 61, and this is your selected section. So we will work with this section and test it out, because every time in the design, every time you make an assumption and select a section, a steel section, you always have to verify and see if it's adequate or not. So then you go to page 440 and find this section here, which is W14 by 61, and almost at the bottom of the page, you'll find the section, and then across to it, you'll find all these values. You'll find the Rx, which is 5.9. You'll find the Ry, which is 2.45. You will find the BF over T times the thickness, and the H over the T times the width. So you'll find all these four values in this page. Just find the shape, which is the first column, the W14 by 61. Then go across the page to the right, and you will find the axis, x-axis, and y-axis. And below them, you'll find the R, you'll find the I, and you'll find the other values. So then, if you remember, we said we have to compare these values to the lambda. Let me grab my pen here, because I think I will need it. Those values here represent the lambda R, and we'll compare these two to these two. So this here goes with the flange, and those are from the tables, right? Those two values. If you are confused with them, you need to go back to my previous lectures and study them. So it's 0.56 under the radical, the measures of elasticity over Fy. The value is 13.49, just a plug-in chart, right? So this value here is larger. See, like this line here, this value is larger than this. So the flange, the lambda is larger than the ratio here, and so as for the width, the 35.88 is larger than this value, just like what is stated here, and that tells me the section or the column is non-slender. So if the column is non-slender, then we'll follow this procedure. How we find K value? If you remember, we talked about the table, the K table, and how we find the K values. I recommend you to go back to that table and find the value. So we have K sub X and K sub Y. Remember, at K sub X is unbraced and is the strong axis, and KY is the braced and the weak axis. So then if I go back to the table, let's do it now since we're talking about it. So the non-sway, which is the weak, supported, and it's fixed, it's 0.65. And the free sway, unbraced, fixed is 1.2. So if we go back to the problem, we have 1.2 and 0.65. Then we find the slenderness ratio, just a plug-in chug, right? 1.2, that's what we found, times 25, the length of the column, times the 12, because conversion from foot to inches, divided by the Rx that we found here, and that's our slenderness ratio. And you do the same for the y-axis, right? Because we need to see which one controls. Now the larger controls, and we'll take this value. Now to check, the code says we always have to be below the 200, which is the case here, so we are okay. Now, as far as this value here, we said you can go to the table, to table 10.3 and find the value without calculating, do the manual calculation, or you can just plug in chug and find this value. So then our control value, the slenderness ratio, is below this, so we are in elastic buckling mode. Remember, we said if we are larger than this value, excuse me, then our mode should be elastic, but this time is inelastic buckling. So because it's inelastic buckling, we'll have to use this equation. I just copied these equations just because those are kind of hard to read and small. So the FE is what you see here, plug-in chug. The Euler buckling equation, or the slenderness ratio, is what we found here, the 79.5, put it here, and then the 29,000 KSI and pi square, you find Fy, and then you plug it here, and then plug in chug, and you find your stress value, which is 31.45 KSI. Then you take this value and plug it in the general equation, which is phi Pn equal phi, the 0.9 is the phi, times the stress, which is the F sub CR, times the gross area, which is 17.9, is what we found here. And it gives me 500.7.